Hello and welcome to the channel Understanding Concepts of Physics. In case you have not subscribed the channel, just subscribe the channel in case you haven't done, and keep watching the videos in the playlist as all the videos are linked. Just watching a single video will not make a major effect to your studies. Today we are discussing one of the topics of thermodynamics called as Stirling cycle, as you can see on the screen. That is entire thermodynamics topic been discussed in the entire playlist of thermodynamics. I would request that this would be probably the last video of thermodynamics on theoretical aspects. Now let's just quickly start with Stirling cycle. This is going to be again a very short video like previous video for Carnot cycle. In case you have not watched Carnot cycle, Carnot engine, then I would request highly to go visit that video and have a look at Carnot cycle or Carnot engine. Understanding Stirling cycles would be much easier if you have been through Carnot cycle. Now let's just quickly start. Stirling cycle is a cycle which consists of the following four processes. So basically, like how Carnot cycle was a kind of a cyclic process. It was a cyclic process which went through four different phases, four different processes. Stirling cycle is also a cyclic process, and it also goes through four following processes. Let's just see. First process is isothermal expansion, which is similar to Carnot cycle. Isothermal expansion. Isothermal means temperature is constant, so temperature will remain constant in this case. It's an expansion, so volume will increase, and if the volume increases, the pressure decreases. Volume and pressure are always inversely related. This is the graph which is represented by AB in the PV graph. Now the next process is isochoric process. Isochoric process is a process in which the volume is kept constant, and when the volume is kept constant, the pressure the process is such that the volume will remain constant but the pressure will reduce. Now as we know that PV is equal to nRT. This is one of the equations we have been using. This is the ideal gas equation. So if you are keeping the volume constant, N is constant, R is constant, so pressure and temperature will have direct relationship. As in this case, isochoric process, we are reducing the pressure. As the pressure reduces, the temperature will also reduce. So I can just add that up over here. We can just add that up over here, that the temperature can reduce. Okay. This is represented by the graph BC. Then third process is isothermal process, which is similar to Carnot cycle. This first process and the third process remain same for Carnot as well as Stirling. Isothermal means the temperature will remain constant, but compression means the volume is going to reduce. As volume is going to reduce, the pressure is going to increase. Then this is represented by the CD portion of the PV graph. Then next comes the isochoric process. Again, isochoric process is a process in which the volume is kept constant, but here the pressure is going to increase. So as I said, PV is equal to nRT. This is our ideal gas equation. If volume, N, R are kept constant, pressure is directly proportional to temperature. So if pressure increases, the temperature will also increase. So this is represented by dA in the graph. So if you just see the graph of the PV graph or the indicator diagram for a Stirling cycle, you will see that pressure is plotted on the y-axis, volume is on the x-axis, and the process starts at point A, then it goes to B, then C, and then D. So because A to B is an isothermal process, you will find out that this will remain a curve, and this curve should be a gradually decreasing curve, and it should not be a steeper curve. Steeper curve represents adiabatic process. Gradual decreasing curve represents the isothermal process. Note that the volume is V1, pressure is P1, volume is V2, pressure is P2, and then from B to C it is going as constant volume process, isochoric process. So volume will remain constant. That's why you'll see here it is V2, here is also V2. However, the pressure is reducing, so the pressure reduces but the volume remains same. Then from C to D, it's again an isothermal process, but this isothermal process, the volume is going to reduce. It's a compression, and the pressure also increases. And then from D to A, it's again an isochoric process, so it's a straight line going vertically upwards. So the volume is remain constant. So if you see, there was volume was V1, and here the volume is again V1. So this is what the PV graph of this is Stirling cycle is. And again, the area inside the cyclic process gives you work done, so this will be your work done. Now note that where is this Stirling cycle used? Now reverse Stirling cycle. So if we run this cycle in reverse order, then reverse Stirling cycle is used in cryogenics. Now cryogenics, what is this cryogenics? Cryogenics is a field where we study at very low temperatures. So if we wish to attain very low temperatures, like near to 0 Kelvin, near to 0 Kelvin, then we generally use reverse of Stirling cycle in order to attain 0 Kelvin, near to 0 Kelvin, because 0 Kelvin is never attainable. So you can reach very near to 0 Kelvin and never exactly at 0 Kelvin. So that's why that makes so special of Stirling cycle, that it is used in cryogenics. So cryogenics is a field where it's a study at very low temperatures. So I hope you have understood the key aspects of what Stirling cycle is. And in case you are still with me, subscribe the channel in case you haven't done so, and kindly watch the videos in a series, in a playlist, to make yourself understand the concepts of physics in a better manner. Thank you so much. Have a nice day. Bye.